Question number 1, we have a square. Answer choice number 1 says that CA is perpendicular to AS, which means where CA and AS intersect, they form a 90-degree angle. That is true when we have a square, because one of our properties of squares is that it has right angles in the corner angles. AH is equal to CS. That's one of our properties of squares. That squares have congruent diagonals. So that is true. CA is perpendicular to SH. That's not true. CA and SH don't intersect. CA and SH are parallel to each other. Answer choice 4 is true because CA, AS, SH, and CH are all equal to each other because a square is equilateral. Here we have the construction of an angle bisector. Answer choice 1 says measure of angle ABD, so that's right here, is half of CBD. CBD is here. That's not true. Those are both halves that are equal to each other. This is not half of this. These are equal halves of the whole angle. Angle ABD is equal to the measure of angle CBD. This is true. These are both halves of the whole angle, and they are equal to each other. Answer choice 3 says angle ABD is equal to ABC. That's not true. Angle ABC is double angle ABD. And answer choice 4 says that angle CBD is equal to half the measure of angle ABD. But that's not true. Both of these are equal halves to each other. If we have a line N and both lines L and M are perpendicular to this line N, then L and M have to be parallel to each other. Two lines perpendicular to the same line are parallel. Which of the statements is not true? AC is equal to BC. AC and BC are both radii of the equally sized circles. AC is a radius of circle A. BC is a radius of circle B. So that is true. AC is equal BD. Once again, AC is a radius of circle A. BD is a radius of circle B. So that is true. They are the same. CD is equal to AB. That's true. We have no reason to believe CD is equal in length to AB. 4, ABD is an equilateral triangle. That is true because all the sides are made up of radii of the circle. AB and AD are a radii of circle A, and BD is a radius of circle. MO bisects angle LMN. So it's being split into two equal parts. Measure of angle LMO is 15x minus 42. And measure of angle NMO is x plus 56. Both of these halves of the angle are in fact equal to each other. If we subtract x on both sides, that is 14x minus 42 equals to 56. And then if we're adding 42 to both sides, we have 14x is equal to 98. And then finally, if we divide both sides by 14, we have x is equal to 7. Now we need to find the measurement of angle LMN, which is the whole big angle. So let's plug in. I'm going to plug in this side first. 15 times 7 minus 42. And that gives me 63. And we can plug into this side too if we want. But we know it also has to be 63 because the angle is bisected, so it's being split into 2 equal parts. So together, both 63-degree parts make a whole 126-degree angle. Point C is in between A and B. AB, the whole line segment, is 3x. BC is x plus 5. And AC is 24. Is C the midpoint of AB? We know that this part and this part together, the AC part and the CB part together, make the whole line segment AB. So if I put the 24 part and the x plus 5 part together, that makes the whole line segment, which is 3x. 24 and 5 is 29. If I subtract x from both sides, we have 29 is equal to 2x. And if we divide both sides by 2, we have x is equal to 14.5. 14.5 plus 5 is 19.5. 3 times 14.5 is 43.5. Let's check if this works out. So this plus this is 43.5, so that's all good. But to answer the question, this half and this half are not the same. They're not halves. So C is not the midpoint. C is not the midpoint of AB. AC is not equal to CB. So the line segment is not split equally. When you do have an explanation question, you do have to explain in words. Your work can be there to back it up, but you do have to explain in words. For this next one over here, we're actually going to be constructing the midpoint. We talked about midpoint in the last question. Now we're going to be constructing it. So we're going to make a perpendicular bisector. Perpendicular bisector splits down the middle. It bisects. To make a perpendicular bisector, we're going to open up from one endpoint to the other endpoint, trying to be as accurate as possible on the computer. And I'm going to swing a circle. And then without changing my distance, I'm going to go over to the other endpoint. And I'm going to make an equally sized circle. right through those two intersection points. I'm going to make my perpendicular bisector. And now we have located the midpoint, where it splits the line segment equally into two congruent parts. I can say, because I labeled my midpoint M, there's lots of things you can say here. I can say that AM is congruent to BM. Since it's a perpendicular bisector, I can say right angles are created here. So I can say that AB is perpendicular to the perpendicular bisector. Or you can add in more points and you can actually say what the angles are. Some people added in point D and said angle AMD and angle BMD are right angles. You can definitely do that as well. There was a variety of things that you could have said here. It just had to be two valid conclusions. I did take that as the midpoint of AB, but that's not a conclusion. That was the question. So that's actually not a conclusion that you drew. It was told to you in the question. Okay. For this one over here, we're going to make a perpendicular line that passes through the given point. So we're going to start off with our compass on the point that we wanted to pass through. And we can make a circle. All we need, I should say, is for it to hit the line in two spots. And that's where my compass is going to go next. It's going to go on one, and then it's going to go on the other. You can keep the same distance. I just like to open up to the other endpoint, but you definitely can keep the same distance. Circle here. And then on the other intersection point, circle here. And right through where those circles intersect, we're going to draw our perpendicular line. Notice how it should come really close to passing through point P. And it's perpendicular to AB, meaning that right angles are formed where the two lines intersect. Second part is to add to this construction to make the line parallel to AB. So if we have two lines that are perpendicular to the same line, that will mean that those lines are parallel. So we already have AB perpendicular to the perpendicular line that we just constructed. So what we need to do is we just need to construct another perpendicular line to this line as well. If we make another line perpendicular to this line, it'll be parallel to the original. So what I'm going to do is I'm going to take my compass and I'm going to put it back on point P because I want another perpendicular line through this point. This time, when I make my first arc or my first circle, it's the same thing. I just needed to hit the line in two spots, but I needed to hit the line that I just constructed. And notice how that circle I just made does hit the line that we constructed in two spots. Once again, you can use the same distance, but I just like to open up to the intersection. Swing a circle on the other intersection point. We'll swing the same circle. And right through those intersection points, I have my line that is perpendicular to our perpendicular line that we constructed before. And since the new line that we just constructed and AB are both perpendicular to the same line, that ensures that they have to be parallel to each other. Okay, for the next part, we are constructing an equilateral triangle. Inscribed in AB. I'm going to do this the way that we did it in class. What I'm doing first is I'm putting my compass on the center of the circle so I could measure the radius. To make it more clear, I'll just draw in a radius. I'm going to go over to the point where the radius touches the circle. And I'm going to make a circle. Once again, this is the length of the measurement of the radius. There's 2 spots where the circle hits the original circle. I'm going to go over to each of them, but I'll go over to the top one first, I guess. Doesn't matter. Swing another circle. Go over to the next place where it hit the original circle. Swing that circle. Let's go over to the next spot. And remember, this starts from a hexagon construction, so we want 6 equally sized circles around the original circle. So that's going to be 7 in total. 6 equally sized circles plus, oops, the original circle. So I got one more to go. There we go. And now, instead of connecting all 6 of the flower petals together, we're just going to connect 3 of them together. Every other one, you could have started with a different one. It just would have been facing a different way. But here we have an equilateral triangle in green over there, inscribed in circle A. I know that the triangle is equilateral. I know triangle is equilateral because I made 6 equally sized circles in this construction. All the sides of the triangle are the length of circle A's radius. Therefore, all the sides are equal. Okay, we're going to construct the line of reflection. I was super lenient for this one, but in order to get full credit, you do have to connect the points together. If you don't connect the points together, you don't have a line segment to make the perpendicular bisector of. And remember, we are perpendicular bisecting these corresponding points from the pre-image and the image because the line of reflection is supposed to be exactly in the middle of the 2 shapes. So that's the bisector part. And also remember that when you do a reflection, the points of the one figure move perpendicularly in a perpendicular direction over the line of reflection. So that's why we're doing a perpendicular bisector. Okay, so in order to be super, super accurate, we should do this again. Also for another pair of corresponding points. So I'm going to do it one more time. And it should, end up being the same line of reflection as the green line that we just had. So when I make this red line now, it should overlap the green line. There we go. And this one's going to be a little bit big. It's going to be a little bit, oops, off my paper here. So you're not going to be able to see my top intersection point. But that's okay. I can see it. You're just not going to be able to see it. And notice how the line of reflection is the same as the one we found before. And just to be as accurate as possible, you should do it with 2 pairs of corresponding points. But once again, was super lenient. On the Regents exam, 2 pairs. Okay. Over here for the bonus, we're going to be constructing a 30-degree angle. So I can get a 30-degree angle from a 60-degree angle, and I can get a 60-degree angle from an equilateral triangle. So I'm just measuring the length of this line segment. And you can make full circles, but I'm just making little arcs. And those were both made using the length of AB. So this is now an equilateral triangle. And now I'm going to bisect one of the angles. I'll just bisect angle A. In order to bisect angle A, I'm going to put my compass on angle A. And I'm just going to make a circle. The circle itself doesn't matter. It just needs to hit the angle in 2 spots. Now you can keep the same distance, but once again, I just like to open up to intersections. Okay, so that's good. Circle on one intersection point. Circle on the other intersection point. Right through those 2 intersection points is an angle bisector. So now we have taken the 60-degree angle and we've cut it in half. So this is 30 degrees and this is 30 degrees as well.